Germany, 1911. A meteorologist named Alfred Wegener was browsing through some books when something caught his eye. A list of identical plant and animal fossils that had been found on opposite sides of the Atlantic Ocean. Wegener was intrigued. How could the same species have gotten from one part of the world to another? He examined the eastern coast of South America and the western coast of Africa, and was struck how the shapes of the two coastlines might fit together. The more he looked, the more links he found. Species of land mammals in East Africa also inhabited the island of Madagascar. How did that happen? Did the animals evolve in both places at once? Or did they somehow cross from one land to the other, swimming hundreds of miles across the Indian Ocean? And then Wegener saw it all clearly. He realized that all the continents in the world had once formed a giant single landmass that he called Pangaea, from the Greek Pangaia, meaning all earth. It was in Pangaea that the plants and animals found on opposite sides of the world had once shared the same home. Then, over hundreds of millions of years, Pangaea had split apart, and its jigsaw pieces had drifted to their present locations. Wegener called his theory continental drift. Wegener wasn't the first scientist to speculate that the Earth had once been dominated by a supercontinent, but he was the first to pull together all the evidence and make a strong case for it. Unfortunately, his peers weren't very receptive. There was no mechanism to explain how the continents might plow through the oceans. Continental drift was just too incredible to believe. As a result, his discovery was largely ignored. World War II. German U-boats were on the prowl. To track them, the Allied forces developed new sonar methods, and scientists were enlisted to help survey the ocean floor. When the United States entered the war, Harry Hess was a geology professor at Princeton University. But he also happened to be a Navy reservist, so it wasn't long before he found himself in command of an attack transport ship in the Pacific. To help maneuver when coming in for a beach landing, Hess's ship was equipped with a depth sounder. Now, still being a geologist at heart, he used the sounder to measure the depth of the ocean floor whenever his ship was out to sea. Now, what he discovered startled him. Until the Second World War, most scientists imagined the bottom of the ocean looked like this: flat, lined with nothing but sediment. But about 2 miles beneath the waves of the Pacific Ocean, Harry Hess discovered something else entirely. Mountains, like these here in California, with deep canyons and trenches, hundreds of high peaks that we now believe were once active volcanoes, and all of this at the bottom of the Pacific Ocean. Surprisingly, though, the discovery of the Pacific mountain range is not what makes Harry Hess part of our Great 100. Now, we'll get to that in a minute. To understand where all this is headed, I'd like to skip ahead to another event that set the geology world buzzing. For years, oceanographers surveying the Atlantic Ocean had taken sonar readings that indicated there was something down there, something big. In 1953, they found out what it was: a 12,000-mile-long mountain range. They called it the Mid-Atlantic Ridge.
The reason it's so great.
To fill us in, I paid a visit to Neil Driscoll, a geologist at the Scripps Institution of Oceanography.
One of the big discoveries that was made was that there was this ridge of underwater volcanoes that stood high above the seafloor.
How high is a mountain in the middle of the Atlantic?
The average seafloor depths are on the order of about 4,000 to 5,000 meters. The mid-ocean ridge sits up at about 2,500 meters. So they sit about 2.5 kilometers on average higher than the surrounding seafloor that's shown here in the deep blue colors.
So that's over a mile high.
Yes.
And that's where Harry Hess comes back into the story. Analyzing core samples and sonar readings from around the Mid-Atlantic Ridge, Hess made an astonishing discovery, a phenomenon almost beyond comprehension. The age of the Atlantic Ocean floor, he determined, was progressively older the further it moved away from the ridge. Harry Hess had discovered that the seafloor was spreading. He concluded that molten rock was being forced up from inside the Earth at the ridge, where it then formed into new crust on the ocean floor. Gradually, it was pushed away on either side as more molten rock continued pushing up from behind it. Hess called his great discovery seafloor spreading.
Harry Hess was in a position that he could bring it all together. Things were spreading apart and new Earth was being generated. But if you did this for long enough, the Earth should grow. And it doesn't.
The Earth doesn't get any bigger.
No. Harry appreciated the fact that if new Earth was being generated in one area, they have to be consumed or recycled in another area.
The process that recycles the crust of the spreading ocean floor back inside the Earth is called subduction. But as our next great discovery revealed, it's all part of a much larger process, perhaps the most powerful force on the face of the Earth.
That the earthquakes...
Hess's discovery that the seafloor was spreading rescued Alfred Wegener's idea of Pangaea from obscurity. Now there was a geological mechanism to explain continental drift.
That's simple.
Once you hear it, it sounds great.
It does sound great.
By the 1960s, both ideas were synthesized into a single theory, the science of plate tectonics. A great discovery that revealed just how complex and dynamic our planet is. Several groups of scientists had concluded that not only is the Earth's crust moving, but the surface of the planet is broken into large, interconnected plates. These plates are constantly in motion, floating on a layer of molten rock in the Earth's mantle.
It seems fantastic. I mean, it seems just too crazy. How could the whole world be sliding around? I can see where people were skeptical.
That's right. But it's the rates your fingernails grow.
That's not very fast. I don't feel a thing.
That's right. Yeah. But cumulatively, it's huge. So here's the thing is geologic timescales is what makes this so important, because if you think of it over a year, you move a few centimeters. If you think over millions of years, you're moving kilometers. About 250 million years ago, all the plates were together in Pangaea.
What about the inside of the Earth? If we were to take a look at the Earth's interior, we would see that the Earth consists of 4 layers. They are the crust, the mantle, the outer core, and the inner core. The crust is the outermost layer of the Earth. It consists of various landforms like mountains, plateaus, volcanoes, etc. The crust also consists of numerous rock plates. The shifting of these plates resulted in the formation of continents. In reality, the crust of the Earth is a very thin layer. It is only 50 kilometers deep. The mantle forms the main mass of the Earth. It is the layer just under the crust. It extends from Moho's discontinuity to a depth of about 2,900 kilometers. The mantle is a partly molten layer and can have temperatures reaching to 4,000 degrees Celsius. The upper layer of the mantle is called the asthenosphere. The hot magma from the asthenosphere travels to the surface of the Earth and escapes as lava from volcanoes. In addition to the asthenosphere, there is a layer known as lithosphere. The crust and the uppermost layer of the mantle together form the lithosphere. While the asthenosphere has a depth of 400 kilometers, the lithosphere extends from 10 to 200 kilometers. The next layer of the Earth is the outer core. This layer is exceedingly hot. It has a temperature of about 5,000 degrees Celsius. The outer core consists mainly of liquid iron. It has a depth of 2,200 kilometers. The core mantle boundary is located at 2,900 kilometers below the surface of the Earth. We now come to the innermost layer of the Earth, the inner core. The inner core has a temperature of around 6,000 degrees Celsius. This is nearly the temperature of the Sun's surface. The inner core has a depth of 1,250 kilometers. Unlike the outer core, the inner core is in solid state. The intense pressure of the layers of the Earth ensures that the inner core remains solid in nature.
There are three main categories of rock that we're going to be studying: igneous rock, sedimentary rock, and metamorphic rock. If these terms look familiar to you, that's because we've actually been using them to describe minerals. We know that igneous is used to describe rocks and minerals that are formed in magma or lava. Sedimentary is used to describe rocks or minerals that are formed basically by minerals kind of cementing together. And metamorphic is used, the word metamorphic is used to describe rocks and minerals that are created under great amounts of heat and pressure. These rocks are created. We're going to start at sedimentary rock. Now, we get to sedimentary rock because of sediments. Sediments are basically small grains of minerals or pebbles or rocks that can basically be collected together or cemented together to form larger rocks. And the way that that happens is that sediments are going to be compacted together. What that means is they're going to be smushed together, and that creates cementation that we have a lot of experience with, especially here in Arizona. So from sedimentary rock, we're going to move to metamorphic rock. We know that metamorphic means that the rock was created under high amounts of heat and pressure. So what probably happens here in this situation is that sedimentary rock somehow ends up really deep underground. And that means that that rock is going to be exposed to heat and pressure that comes from the mantle, that comes from all of the mass that's pushing down on it, that comes from pockets of magma below the Earth's crust. So there's lots of different sources for heat and pressure. And basically, this high heat and high pressure environment causes the minerals within that sedimentary rock to change. So they transform, they undergo chemical reactions and physical reactions that cause them to turn into metamorphic rock. And we're going to learn about specific types of metamorphic rock later on this week as we go through the three rock categories in more detail. So after we get metamorphic rock, we get a little bit of melting. Now this can happen because metamorphic rock is so far underground that it's exposed to a lot of heat. But if that metamorphic rock comes in contact with the really hot mantle or hot pockets of magma, it will also melt. That melting causes it to become magma. Remember that magma is different from lava because magma is still underground. Lava only describes molten rock that has escaped through volcanic activity onto the crust. So we get magma, and eventually that magma is going to cool. And that cooling creates igneous rock. Igneous rock is rock that's created from volcanic activity, so from cooling magma or cooling lava. Now that we have igneous rock, we've got all three major rock categories, but igneous rock doesn't stay igneous rock forever. It can eventually experience a breaking down from weathering and erosion. Weathering is basically the process of taking large pieces of rock and slowly over time degrading them into smaller pieces, into sediments. So we get weathering through chemical reactions, when different types of rocks or different minerals react with each other and cause them to break down. But we can also get mechanical weathering, which is basically exposure to high amounts of wind and other smaller sediments that sort of scrape away at the rock like sandpaper. And erosion is the process of taking those sediments and spreading them across a large area. So moving those sediments away from their original location is erosion. So as you can see here, if you follow the blue arrows, we've come around all the way from sediments to sedimentary rock, to metamorphic rock, to magma, to igneous rock, and then back to sediment. So we've come full circle here.